we discussed the joint distribution of two random variables. We can extend the concept to arbitrary and random variables. All right, so the joint cumulative distribution function JCDF x1, x2 up to xn of n random variables x1, x2 up to xn, and is defined as x1, x2 x sub n is the probability of the joint event that random variable x1 is less than or equal to little x1, and capital X2 is less than or equal to little x2, up to capital Xn less than or equal to little xn, for all x1, x2 up to xn. Okay, all right. So for all variables x1, x2, xn on the real line. So this is just with the same idea. We can extend the joint CDF to n random variables. And so marginal CDFs f sub x sub I of x sub I for I from 1 to n of x1, x2, xn can be computed from their joint CDF. Okay. As follows. F x1, x1. Okay, can be computed that by limit of x2 goes to infinity up to xn goes to infinity of f x1, x2 up to xn. Okay, so that is f of x1 infinity up to infinity. Okay, you can marginalize. All right, and the last one. Okay, so the marginal CDF of x sub n is the limit x1 goes to infinity up to xn minus 1 goes to infinity, and the f of x1, x2, xn. So that would be f of infinity, but xn. Okay. Okay, and for n discrete random variables x1, x2, xn. We can define for n discrete random variables, taking one of the values a, I1, AIN, respectively. We can define the joint probability mass function as little p and AI1, AI2, AIN, okay, defined to be the probability. The x1 is equal to AI1, x2 equal to AI2, xn equal to AIN. Okay, and there marginal PMF can be computed as follows. At little p x1 AI1 is the summation, okay, for all I2 up to IN, the P of AI1, AI2 up to AIN. Okay. So you sum over all possible values for random variables except 2 up to except n. Okay. And the last one, Pxn, is the summation for I1 to In minus 1, probability of AI1, AI2, AIN. Okay. All right, and the unrandom variables x1, x2, up to xn are called jointly absolutely continuous. Okay, if there exists a non-negative and integrable function little f x1, x2 up to xn on the n-dimensional Euclidean space Rn. Okay, such that for any n cell I1 Cartesian product I2 Cartesian product up to In in Rn where I sub I are intervals of the real line. Okay, so such a Cartesian product is called an n cell. Okay, so for any n cell, the probability that x1 is in I1, x2 is in I2, up to xn is in In. Okay, sometimes we denote it as the random vector. Okay, the random vector is in the n cell. Okay, right, and is the integral okay, this integral. And because the integrand is non-negative, so this integral can be evaluated by repeating the integral, okay, in any order, okay, in any order. All right, and in this case, f of x1, x2 up to xn is called a probability, called a joint probability density function, JPDF of x sub 1, x sub 2 up to x sub n. Okay. The joint CDF of x1, x2 up to xn can be computed as okay, we know this is the probability that x1 is less than x1, x2 is less than equal to x2, up to xn less than equal to xn. And this is the probability that the random vector is in this n cell. Okay, so it's this n cell, right? And so that would be the integral f of u1, u2 up to un, and du1, du2 up to dun. Okay. So we can evaluate how to compute the joint CDF of this random variable by n-fold integral over the joint probability density function. Okay? And also, in this case, each x sub I is absolutely continuous with a PDF okay, to be so you integrate over x2 up to xn in the whole range of this variable. Okay. Okay. So please show it at home. All right. So the proof will be similar to we have given for the case of two random variables for n equal to 2. And so it can be extended to arbitrary n. Okay. Any questions? Okay. Right. So if no further questions, then I will go to the second sections of chapter 6. So we will consider independent random variables. We define independent discrete random variables in chapter 4 before, but here we will discuss the general case. Okay. Again, we start with two random variables. Right. So now two random variables, x and y, are said to be independent if for any interval I and j, okay, so for any intervals I and j of the real line, the probability that x is in I and y is in j. All right, so the probability of this joint event is equal to the product of the probability of each event. Okay. Okay, so to check that two random variables are independent of each other, we have to check that, the the equality is true for any interval I and the interval j. Okay, so we have to check that. All right, and we can simplify this work a little bit, okay, by proof the following theorem. Right, so it says that two random variables, x and y, are independent if and only if for all real numbers a and b, that the probability that x less than equal to a, y less than equal to b is equal to probability of x less than equal to a times the probability that y is less than equal to b. Okay. So this is saying that that p x is in y is in this equal to So the theorem says that if we just check some special types of intervals, okay, so this type of interval is from minus infinity up to a, so this is open half closed interval, okay. And another useful information is that this probability is actually the joint CDF of x and y, and this is the marginal CDF of x and the marginal CDF of y. So to check whether two random variables x and y to be independent, we only need to check that the joint CDF of x and y is equal to the product of their marginal CDF. That would be quite more treatable, right? Okay, because we can find the joint CDF, all right, of x and y, and use the marginalization to find the marginal CDF, right? And then to check whether this joint CDF is the product of the marginal CDF. If this is true, then by this theorem, we will prove shortly that x and y are statistically independent of each other. And we don't need to check general interval I and j, right? Because this is more complex, to check. Okay, so this theorem is useful. Okay. Any questions about the meaning of the statement of this theorem? Any questions? Okay, so if no question, then and the proof. All right, this part. Okay, if x and y are statistically independent, then of course this is true. Why? Because this is an interval. This is also an interval. Okay, so this is from the definition of independence. Okay, so what we need is to prove the backward direction. Okay, so so basically we will apply the continuity property of probability function. So first of all, so there are special types of intervals, but from that we can prove the following: the probability that x less than a and y less than or equal to b. So now we change it a little bit, right? So is that x is less than a, right? And we keep here is less than or equal to b. All right, and this is actually the limiter of the probability that x is less than or equal to a minus n1 and y. Okay. What is the reason? Why? The reason is that the event go up, right? To x less than a as n go up to infinity. Okay, so since the is go up, because as n go up, this is smaller and smaller, right? And so a minus 1 over n will approach to a from the left-hand side, but never reach a, right? Never reach a. Okay? And so it's going up, and the limiter of this monotone increasing sequence of event is just x, is this event. All right, so that x a minus n1 intersect y less than or equal to b will go up to x less than a intersect y b as n go up. Okay, and so that we have this by the continuity property of the probability function. P. Okay? So we have that. Any questions? So we apply the continuity of the probability function several times, right? When we investigate the properties of a distribution function, right? The cumulative distribution function before. So we have that. Okay, and so now this is limiter. But we know it fits to this. So it's less than or equal to a minus n1, y less than or equal to b. So by this property, because we assume we have this property, so that we can now, this joint probability becomes the product of respective probability. Okay? From here. All right? And again, now, by continuity, okay? by the continuity property of the probability function, this is the probability of x less than a, right? So this one goes to here, and this is probability y less than b. So we just proved that if we change the less than equal equality sign into the strict equality sign, we have the same property, that the joint probability becomes to the product of respective probability. Okay? Any questions? So once again, we apply here. Okay. Maybe I will say the same. Oh, no. Yep, the last one, by the continuity property. So this one is from the given property, right? The property of P. Okay, and similarly, so with a similar argument, again, also by the continuity properties of the probability function, that probability of x less than or equal to a, but y is less than b. All right, this time is here, and we can b, okay? And also, the probability of this joint event is equal to the product of the respective probabilities. Okay, here. Okay, so we have these two results. Okay. By similar argument here, right? Okay. Right. So, for example, the sequence of events we will approach to this one will be x less than or equal to a minus n1 intersect y less than or equal to b minus n1. Will go up to x less than a, y less than b, and go up to infinity. Okay, so this event is the limit of this mountain increasing sequence of events. Okay. So the limit of the probability is equal to the probability of this event. Okay. And because here we have less than equal to, less than equal to, so we can apply this property. Right. All right. Okay. So now for I is equal to A1, A2, and J is equal to B1, B2. Right? So suppose I and J are two finite closed interval. Right? The probability that X is in A1, A2, and the y is in B1, B2. Okay. Okay, and so if we, this is saying that the xy is in A1, A2, B1, B2. Okay. And so when we look at here, which I just draw an example. For example, here, suppose that we have okay, so here this is A1, A2, we have B1, B2. I'm sorry, no. I draw it carefully. All right, so suppose this is A1 and this is A2, and we have B1 and the B2 here. Okay, we have this one. And the square is here, including the boundary, right? So it's including the boundary. Okay, so this one is A1, A2, Cartesian product with B1, B2. Okay, and the point here is A2, B2, and the point here is A1, B1. The point is here is A2, B1. Here it's A1, B2. All right. Now we can, sorry. So it's in all right. Now, first of all, the region. So we can see the region. I will maybe I found right here. So A1, A2, B1, B2. So this region is that we can think about that up to so the whole region, okay, from this point up to the whole left and the downside, okay, so that would be A2, B2, okay. This is the area, and then we will delete the low part, right? So we may delete the low part. Say that so would be inclusion Okay. And the minus. So we will delete this one, and when we delete this part will be A2 and B1. So cross B1. Okay. So when we delete this part, okay, so it's from minus infinity to up to A2, and this is from minus infinity to B1. So it's this part. Okay, so the whole part, delete this part, and also we have to delete again another one is this part. So probably I use different color. So that would be okay. And the minus that we will have A1 cross and oh, by the way, because I have to remove because I have to include the age, right? So so that B1, sorry. So B1 will be an open one. Okay, so I have to. This is open, but this is solid. Okay, this is included. Okay, so this will be open side. And for here, the green one is with this one, but without the boundary. So this is dash, and this is boundary. Okay. So we would have A1 times B1, B2. Okay, minus 1 here. Okay, so this probability it will be equal to this one, but minus the probability of xy in A1. Oh, okay, sorry. A2 minus B1, okay, and the minus probability of xy in the A1 times B1, B2. This probability. Okay? But the green one, but all right, it's actually equal to the orange one. Okay, the orange one. So the orange one would be minus infinity A1. Okay, times minus infinity B2 minus the red one. So the red one would be here. Okay, so will be minus infinity A1 times minus infinity B1 bar. Okay, and so this one, so we have probability that xy is in. So I will write it in a more convenient way. This is less than equal to A2. Y is less than equal to B2. Okay, and minus this one is probability that x is less than equal to A2, but y is less than B1. And the minus, all right? So this is the probability that xy is in the bigger one, minus infinity A1 times minus infinity B2, okay, minus probability that xy is in minus infinity of A1 times minus infinity of B1 open, okay, this one. And what is that? This is equal to probability that x is less than A1, y is less than equal to B2. Okay, and this probability is probability that x is less than A1 and y is less than B1. Okay. Okay. All right. So finally, we combine them together. So we have less than B1 minus probability, the third one, A1 and B2. Plus probability. Okay. Right. So the joint probability becomes to linear combination of these four probabilities. And we have just shown that this is right. This is from the original given condition because we have assumed that this is true, right? And we also prove the other three types of joint probability so they can become to the product of respective event, of the probability of respective event. Okay, so now we can split them. Okay, Okay, and this 4 right can be factorized into okay. Any questions? And so this is a probability that because this x will be less than equal to a2, but we move for x less than a1, so would be x would be greater than equal to a1, and probability here y is b1, b2. So this is probability that the x is in a okay. So if I and j are finite cross intervals, then we have shown that this joint probability is equal to the product of the respective probability. Okay, right. Okay, and the similar argument applies to arbitrary intervals I and ij. Okay, so this complete the proof. Okay. Of course, you have to check other types of intervals, but the idea will be the same. Okay, similar to the ideas here. Okay, so you can just draw the pictures like this one to see. Okay, so this is a very elementary proof, a detailed proof of that. Okay, so we have this property. Okay. All right, so now there are quite a few applications of this theorem. Two discrete random variables, x and y, are independent if and only if their joint PMF Pxy is the product of their marginal PMFs i.e. the P of xy equal to Pxx Pyy for all xy. Okay. So that the theorem will be useful because we can take the advantage of the joint probability mass function of two discrete random variables. Okay. So from the joint probability mass functions, we can compute the layer marginal probability mass functions. Okay. And to check if the joint PMF is equal to the product of these two marginal PMFs. That's all. If not, then X and Y are not independent. Okay. All right. So the proof we go this direction. Okay. So by letting I equal to XX and J equal to YY. Okay. XX, YY, just special types of closed intervals. Okay. So we have, okay, the P of XY by definition is probability of X equal to little x, capital Y equal to small y here. And this is probability that X is in XX, Y is in YY. Okay. All right. And because X, Y are independent, so this joint probability becomes to the product of these two probability. All right. Yeah. And this is probability of X equal to X, probability of Y equal to Y. And that would be P X X, P Y Y. Okay? And we're done. Now, reverse direction. Now for any okay, so assume that AI and BJ are the ranges of X and Y respectively. Okay? So we index the possible value of X by I. So it's A sub I. A sub I are possible values of random variable X. And B sub J are possible values of random variable Y. Okay. Okay, so now for any intervals I and J, okay, the probability that X in I and the Y in J. So what is that? Which means that this summation of I such that AI is in I, summation of J, and the BJ is in J, of P of AI and the BJ. Is that okay? Now, because the joint PMF is the product of marginal PMF, so this is I such that AI in I. Summation J index such as Bj is in J. And the Px AI, Py Bj. And now, because we can split this function into a product of two marginal functions, so that this becomes two. So the sum of product become two product of sum. So this is AI in I, Px AI, summation J, Bj in capital J, and P Ty Bj. Okay? This is possible because we have sum of product. This is a product. Okay, but what is that? This is actually probability at x is in I times probability of y in j. Right? The event x in I is all, maybe I will write it gradually. Maybe it's okay. All right. By definition, right? The PMF is that. And what is that? The summation. This is actually is the probability, the union of I, such as AI in I, P. Okay, it's the joint union. Bj in capital J. But this, sorry, no P. Okay. By using the countable additivity, okay. So, but the union, this union is actually equal to x is in I, the same. Why? Because x takes value at a sub I only. Okay, so, and this is P of y in J. Okay. Okay, and so we prove what we want already here. So the joint probability is equal to the product of the probability of respective event. Okay, so we've done. So that is for two discrete case. Now, theorem 6.2.c. All right. Now we are two jointly, absolutely continuous random variables x and y. So now we consider two random variables. They have a joint PDF. So if we have two jointly absolutely continuous random variable x and y with a joint PDF called f of xy, right? are independent, right? If and only if and only if f of xy, if only if the joint PDF is the product of the marginal PDF, okay, for almost all xy in x and y on the real lines. Okay. So for almost all means that you may find points, okay, such that some point x and y point such that this is not true. But the area of this point would be 0. Okay, so the equality may not be true for points scattering over the plane. Okay. Can be a line, that's fine, because a line has 0 area. Okay. So it's not required to be equal for all xy, not necessary. Okay? It's not necessary. Just almost all. Okay. So I will explain that what we mean for almost all. Okay? We mean if we collect all points such that f of xy not equal to this product. Okay, if we collect them together, then the area of this set is equal to 0. Okay? So the meaning of almost all means that you are allowed to have the inequality for some points. And the set of all these points, when you put together, the area of this set is 0. Okay? So that is the meaning of almost all. Any questions about almost all? Okay. No? Prove the direction here. Now for any intervals I and j, we have, because x and y are independent, right? We assume they are independent. So we know the joint probability, right? The joint probability, right, is equal to the product of the probability of respective events. All right, and as we just shown before, when x and y are jointly absolute continuous, then x is absolute continuous Y is also absolute continuous, right? And they have respective PDF, and the PDF, right? So this is actually can be computed, right? So this, by definition of a PDF, this probability is that we integrate the PDF over the interval I, and this will be obtained by Y, right? And then we will combine them together. Okay. As a twofold integral. All right? But we know that they are jointly X and Y are jointly absolutely continuous with a PDF f of xy. So this probability can be computed in this way. Okay? And so here we have these two. Okay? So the identity, so this integral is equal to this integral. And the integrand, they are all non-negative and integrable. So that x and y should be equal to this one for almost all xy in between minus infinity and infinity. Okay, because as I mentioned before, okay, if two random variables has a joint PDF, then it will have infinite many joint PDF. But any those joint PDF will be equal to each other for almost all x and y. Okay. The reason is that if they are not equal in some set with area greater than 0, then we can prove that over that area, we cannot establish the identity. Okay. So all right. Now, for any, this part is easy. For any interval ij, we have the probability of x in I, y in j is equal to ij fx fy dx dy. Why? Because their joint PDF is equal to this product. So we just place this product into here. And because this is separable, so that we can reduce this double integral into the product of the single integral here. Okay, and that is probability that s equal in I, probability in j. Okay, and we have done. So the reverse part is easy. Okay, and so that would be So theorem 6.2.A, point B, point C, these three theorems are useful, very useful to identify whether two random variables are independent. Okay, independent. Okay. In general case, if you don't know x and y to be both discrete, or if you don't know x, y are jointly absolute continuous, then you have to apply this one. Okay, you have to show that their joint CDF is equal to the product of their marginal CDF. All right, to justify that the x and y are statistically independent. But if x and y are discrete, then you can use the joint probability mass function to justify them. And if x and y are jointly absolutely continuous, then you can use their joint PDF to check their independence. All right. So this three theorem provides tools for you to justify the independence of two random variables. Okay. All right. So, and okay. Oh, all right. So let's take a break for 5 minutes. Okay. Hey. Okay. I'm sorry, there's a typo error. When I talk about how to compute the marginal PDF from joint PDF. So suppose that n random variables x1 up to xn has a joint PDF. Then the marginal PDF for x sub I can be obtained by integration over all the variable except x sub I. Okay, and this is a mistake because that when I write the differential here, this is only good for I equal to 1. Okay, so we have to exclude only this x sub I. Okay, so please correct the differential parts of this integral. Okay. All right. The textbook provide proposition 6.2.1. Okay. I will say AC, but it consists of two parts. Right. So we say two jointly, absolutely continuous random variables x and y are independent if and only if they are non-negative and integrable functions h and g on the real line such that f of x, y, so is equal to, I think I forget to, with a joint PDF. Sorry, I forgot to put this part. H of x and g of y for almost all x, y in between minus infinity and infinity. So this one is a little bit weakened than here. Okay. So it's not necessary to find out the marginal PDF. Well, you just check if if the joint PDF of x and y can be written as the product of a function of x and a function of y here. And it's very important that this is true for almost all x and y. As you may observe in chapter 5, many PDF is defined piecewisely. For example, for exponential PDF, it is defined in two pieces. first of all, okay, let me see here. An exponential PDF is defined as follows. F of x is equal to, for all x and 0. Okay? So exponential PDF is defined piecewisely. You can't write a single formula for PDF for x over the whole real line. Okay, this is true for normal PDF. That's fine. Okay, normal PDF, you have a formula, all right, a single formula, so you can define it only one piece. But for exponential PDF, you have to define it in two pieces. This is same as for gamma distribution. For gamma probability density function, you have to define it for x greater than 0 and x is less than or equal to 0. Okay. So, right. And but the identity here is that it regards this h of x is the function defined on the whole real line. Okay. And the g of y is a function defined on the whole real line. So it's the product of two functions defined on the whole real lines. Okay? This is very important to know that. Because in applications, because many students, when apply the propositions, they tend to check only something that have non-zero density value, probability density value, and forget the other part. Okay, this is quite often. All right, and then in that case, you will misuse the proposition. Okay. Okay. So this is why my advice for you when you apply the proposition of the previous proposition. Okay. Right. When you have identity here, okay, they should be valid as a function on the whole plane. Okay. Okay, so the proof. Okay, so this part that's by. Oh, I use theorem. Okay, actually I should use proposition. Okay, I didn't correct my notes. Okay. But I prefer, for consistency, I prefer to use proposition. I'm sorry again. And again, for the proposition 6.2.8, okay? So please correct it. So by proposition 6.2.c, okay, we set h of x to be the PDF of x, and we set, set, G of y. Okay, so we have done. Now, the reverse direction. Now, since 1 is equal to right, so suppose the joint PDF is the product of these two functions. Okay, and so that would be right. So you can split the double integral. All right, and we call this as C1 times C2. Okay, where C1 is just equal to the first integral, and C2 is the value of the second integral. Right? Right? Since we have that, and also the marginal PDF can be computed, right? This way, right? Because this is the together is the joint PDF, right? So we marginalize that, and so this is h of x times C2. Okay, and similarly, f of x, fy, the PDF of y would be so this is C1 and the G of y. Okay? All right, so altogether, so we have so now we have the f of xy is equal to h of x and g of y. But because C1 times C2 equal to 1, so this is C1 times C2 of h of x, g of y. And we have C2 h of x, C1 g of y, and this is f of x, f of y. Okay. Okay, for almost all okay. So now by proposition 6.2.c, x and y, okay, okay, so the reverse direction. Now we prove this, right? And so x and y are independent. Okay. So with the help of proposition 6.2.c, we can prove the first part of proposition 6.2.1. And I'm sorry. For the discrete case, two discrete random variables. Sorry. So, two discrete random variables x and y are independent if and only if they are non-negative functions h and g on the real line okay, such that the joint PMF of x and y is equal to h of x and g of y for xy in R. So now, different from the absolute continuous case, that the equality should be valid for all xy in R. Okay, no exception. Okay, and the proof. Okay, so as an exercise. So you can use the same argument as in the AC part, but you have to use the proposition 6.2.b, okay, instead of proposition 6.2.c, okay, to show it. Any questions? Okay, so now the following will be extension. So we talk a lot about the independence of two random values. Now we will extend to a collection of random variables. Okay. Now unrandom variables, x1, x2 up to xn, are said to be independent if for any intervals I1, I2, in of real lines the joint probability x1 is in I1, x2 is in I2, xn is in In. Right? So the joint probability can be and equal to the product of the probability of respective event. Okay? And remark, proposition 6.2a, 6.2b, 6.2c can be extended to the case of n random variables. Okay? One, that x1, x2, xn are independent random variables if and only if their joint CDF can be written as the product of the marginal CDF. Okay? So the first, so proposition 6.2.a can be extended to this one. The second, x1, x2, Sn are independent discrete random variables if and only if p of x1, x2 up to xn. So their PMF is the product of their marginal PMF okay. And third one, okay, so x1, x2, x up to xn are independent, jointly absolutely continuous random variables with a joint PDF. x1, x2 up to xn, if and only if the disjoint PDF is equal to the product of their marginal PDF for almost all variables